Log on, tune in, find out. Another good idea from Cambridge.
From 2 to 3 and then from 3:30 to 4:30 with a coffee break. And the first speaker today is Faraco from Universidad, Autonoma, and we're speaking about stability Calderon problem into the
So thanks Seava, and thanks Seava and Gunther for inviting me here. I organized 2 special semesters last year in Madrid, and I know how tremendous effort it is, and then it is very nice now to be here and being just a participant and being able to have discussions and concentrate all my time in research. So the topic is stability of the Calderon problem in 2D, which I guess the Calderon problem itself has been a recurring topic during this couple of months, but still I will remember the basic statement and a brief history. So, mathematical framework is as follows. I will be having a domain, which on purpose I make with this crazy boundary, because it will be part of the talk. And then I look at so there is a conductivity here, say for the time being a function gamma, and then I look at the Dirichlet problem on this domain, with some boundary measurements. And then the inverse problem is to see if this gamma is unknown, and from what I measure in the boundary, I would like to determine what is gamma. So these measurements in the boundary, as we were hinted by Calderon already 30 years ago, are given by the so-called Dirichlet to Neumann map. So this map takes this G, which is an element in the boundary, and map it to the current whenever I can define n is the normal component of the domain. So I can give this definition whenever I have a normal component, but I can also define it weakly. So I define this action as an operator in h minus 1/2 as this integral. And now this is in h 1/2, and this element is in h minus 1/2. Okay? And what we want to know is whether if I know this operator, which is in the boundary, I can determine the gamma. Okay?
It's probably not J of G, is it?
Perfect. Thank you. And this psi will be an extension on Thanks. Okay, and then the question is the following. This first question: suppose I have 2 different conductivities, and then these two operators, these 2 Dirichlet to Neumann map agree. Whether it's true that the 2 conductivities would be the same. Okay. To start with, let me assume that this is a function which a priori, so k is a constant greater than 1, and this function is bounded above and is bounded away from 0. And I express it in this way. And k would represent the ellipticity of the problem. Okay, so in this setting it's a strongly elliptic problem. Okay. So unfortunately there is a question mark there. And this problem is it's very old and it was started by Calderon, and I'm not going to review all the history, but some of the main items. So he formulated the problem and solved the linearized version. And suggests to use harmonic exponentials. Then an important year was 1987, where Sylvester and Ullmann solve the problem actually when we are in dimension greater than 3 and when the conductivity has some regularity. So gamma has two derivatives, but apart from this breakthrough, they introduce what is the main tool now in attacking this problem, which are the so-called complex geometric optic solutions. So, and introduce CGO solutions. So CGO stands for complex geometric optics. So this, in some sense, tries to follow the ideas from Calderon, looking for harmonic exponentials, but harmonic exponentials wouldn't be solutions of your more general divergence type PD. So they look for solutions which looks in this way. They are complex value, so they are given by some complex frequency, and they have an amplitude, AX, and a remainder. Okay, and this is amplitude, and this is remainder. And the remainder, as its name says, the idea is that it will go to 0. So that in the limit, when this frequency is high, we will have the complex exponentials. Okay? So in n equal to 3, greater than 3, there has been a lot of research in this direction, also extended to the local problem and to others, but I think the best result by now is from this summer. So now it should put 2011, so that you don't think we'll go back in time. And it's from Tataru, Daniel Tataru, who says Calderon OK for gamma C1. One derivative. So with one derivative we know, with this and that it's not clear. Okay, so what I said here is solve for n greater than 3, and in fact the method doesn't extend as it is to dimension 2, where a different approach had to be introduced, and this was done by Nachman, 95. Okay, let's be consistent, so the 19th I don't put before. So Nachman said n equal to 2, two derivatives, Calderon OK, and introduce a different approach, which is called a scattering transform approach, and approach via scattering transform. This was then, so then here the issue was the regularity. We have two derivatives, now in the space 1. And, okay, let me go directly. Brown. I think this is not much after. So this year is correct because this I was in. Okay. Let's leave it there. they could deal with one derivative by following what is called a DD-bar approach. And then in 2006, we get to know that the Calderon problem, the Calderon question, is true for conductivities which are A infinity. So this was done by Kari Astaga and Yassi Paivarinta. N equal to 2, gamma in A infinity, but satisfying the ellipticity bounds up there. Calderon okay. And for my own interest, they introduce as a method quasi-conformal mappings. Okay, and QC maps. Okay. So what I want to discuss is this method and to which extent this can be made stable. Okay. So. Yeah.
It's correct that when you put this boundary, you just define h1 half as the traces of the function from h1, right?
Yeah. Yeah. Okay. Then. Yeah, so maybe I give this funny picture, and I go to question 2, which is the stability of this process. So question 1 is whether the two directional map agree, the two conductivities agree. Question 2 is whether, okay, now I have these two conductivities, gamma 1 and gamma 2, and now I don't know that these directional maps are the same, but I would hope that there is a way to measure the difference between the two conductivities by the difference of the two directional maps. And here let me be vague. Even here I think one could be vague. So now that when two functions are the same, we don't have anything.
B is a constant of function of.
Wait. B would be a function, but just a second. So the first is that this would be in some norm, this would be some norm, and B would be a modulus of continuity. Typically, if it was EFG, we would be happier, but B of t is a function from R to R, and let me just state a modulus of continuity. Okay, so that's what I want to discuss. Now there are bad news and good news. So I think I start with the bad news, and then I tell some good news. So the bad news is that the answer in general is false. Bad news. There is an example, the first example of Alessandrini, who first considered this question in higher dimensions. And then it is like this. So you have these conductivities, and then you put a tiny ball here, and you define gamma h equal to the characteristic function of these balls of radius h plus, say, the characteristic function of the unipole. So it's going to be 2 here and 1 there. Okay? And then in this situation, the directional map, you can compute it directly. You can write it as a Fourier series, and you can find its expression as a Fourier multiplier. And one quickie is that this tends to 0. So here, the canonical norm would be the norm as an operator from h1 half to h minus 1 half. This goes to 0, but we see that the difference, the infinity difference between gamma h and the identity is 1. So at least in general, I cannot pretend to establish this type of inequality with the infinity norm here. Okay, and okay, the abstraction here is regularity, because the coefficients are discontinuous. So if I want an A infinity stability, meaning that I have on the left-hand side the A infinity norm, I cannot expect to have it for discontinuous coefficients. Okay. The other bad news that we have to live with is about the modulus of continuity. So I would love to have there a Lipschitz continuity or something very nice, or at least Heider. But there is a beautiful argument of Mandaje which proves that this is not the case. Okay, so bad news, maybe this is number 1, obstruction to regularity. Number 2, bad modulus of continuity. And this is Mandaje. This argument is very nice. So what he does is he looks on one hand at the set of all direct to Neumann map, and he looks on the other hand at the set of all conductivities. So here are the conductivities with a certain bound. So this is represents the set of conductivities as functions, say in C2 or in the space I want. And they are data separated. Whereas the space of all direct to Neumann maps in the space of operators, they are quite packed. So there is the Landau's identity, and the rest of them, there is one for each conductivity here, but they are quite packed. Okay. In fact, there is an epsilon net. It's a precompact set, and there is an epsilon net. Okay. So what he does is just take this set of conductivities and look which are data separated, and make this data as big as possible, and look at this set of operators and form an epsilon net and make this epsilon as small as possible. And then by comparing the delta, which is going to be large, instead of the epsilon, he gets that the modulus of continuity is logarithmic. Best is logarithmic. So it would be b of t equal to 1 over log 1 over t, and here some power. The power will depend on which regularity you assume on your conductivities a priori. So if they are very smooth, then you will have something, and the less smooth they are, the worse is this power, but anyhow, it has to be logarithmic. Okay? So these two bad news. And then in the plane, I have first good news that, okay, so I need to assume some continuity to have infinity conductivities, and I need to assume some, and the best modulus of continuity I can have is logarithmic. So first good news, let's put it here. So this is a theorem. N equal to 2. Okay, let's put the names. Barceló, save and read 0.7 and n equal to 2. The gammas, they have some control, they are continuous in a mild sense, so that they are either continuous for some epsilon, elliptic, and then we have, in fact, this modulus of continuity, which is also logarithmic.
Don't assume the gamma is above and below.
Elliptic, all the time elliptic. I think all this could be extended to this case where the
uniform elliptic is more than some constant.
Uniform elliptic, yeah. About this, how much it can degenerate, I think the uniqueness proof of, there is a recent paper of Asta, Lassas and Paivarinta, where they have the uniqueness for a degenerate elliptic, where essentially the ellipticity degenerates in a BMO sense, and there I think this proof would work, but we haven't checked. Okay, so here, and here, yeah. And then I have to say this is n equal to 2. Now previously for n greater than 3, this was established by Alessandrini, who started this issue of stability for essentially two derivatives. And as far as I know, the best result is from Heck, who can handle the case of 3/2 derivatives. And I'm not aware that nobody has taken the approach of Tataru. N equal to 2, there was previous work of you and Barceló, another Barceló, and the same Ruiz. Okay. And they did gamma C1 S. Okay? So I have this infinity stability with this continuity, and I could tell you that the example of Alessandrini shows that it's optimal. However, then it would come a natural complaint very fast. So I remember that this example was something like this. So I have 2 here and 1 here, and then I was shrinking this ball, the measure of this ball to 0. So the infinity difference is 1. So what one should try? So this example was bad because here I was putting an infinity. But now if I, instead of a infinity, I change this question mark by a 2, then this example is perfect. It will go to 0 in A2. Okay? So this tells us that these counterexamples to stability based on this continuity are because we insist in having an infinity instability. Okay? Which maybe doesn't make any sense for these continuous coefficients. So next I would look for a stability where instead of an infinity I put there A2. However, I would like to say that I have a result, but there is a third but new. Okay. A third but new is that the instabilities, they don't come only because of a lack of regularity, but they come because of a lack of control on the oscillation. Okay, so third but new comes from G convergence. In fact, already from the argument of Mandaje, you can see that there cannot be stability in general because, okay, unfortunately, I erased this picture a little bit too early. Okay, I have this and I have this. Now, the fact that there exists an epsilon net here, it means that this set is precompact. So if this process of going from the to Neumann map to the conductivities would be continuous, then this precompact set will be mapped to a compact set. And now if I Frechet Kolmogorov, I need to have some control on the A2 modulus of continuity. Okay? So there is an abstract way of deducing from Mandaje that cannot be stability in general, but the more precise way to see this is with the concept of G convergence. And then, so the starting point is this theorem, which at least I learned from a paper of Sandrini and Khabib, which states the following. So suppose I have a sequence of conductivity. I am in this situation, say in the unit disk, and I have here a sigma h, and sigma h is equal to the identity in a annular region around near the boundary, and it's something else here. Okay, and sigma h happens to G converge to the identity, in the sense of Españolo. Then, now I will come to some examples. But before, let me state the result. Lambda sigma h minus lambda of the identity converges to 0 in the operator norm. Okay?
In which part?
L on h1 half. Don't make me write it each time, otherwise I'll get so far. But yeah, I was saying here that I was putting this second question mark here, but in fact I never have done this in practice, and I never have seen it. But maybe it's a good idea to also change here the operator norm. I don't know. On the other hand, in full generality, this Dirichlet normal map only belongs to this space, so I don't know. This I haven't explored. Anyhow, back to this. So we have the G convergence cause the convergence of the corresponding Dirichlet normal map, unless, at least under this condition, that the limiting matrix is the identity, and that the sigma h are equal to the identity in a neighborhood of the boundary. And let me, okay. What is G convergence? G convergence is this concept. It was introduced by Españolo, and it means convergence of the green functions. And in practice, in our setting, it means convergence of the corresponding solutions, strongly in the A2 norm and weakly in the W12 norm. And but the classical example, in fact, the one used by Sandrini and Khabib, is this checkerboard. So I put this inside. So I say I will have 2 here, 1, 1, and then I make this finer and finer. So okay, like this. And then the next, so this will be sigma 1, this will be sigma 2, and the sigma 3 will be the same picture in a smaller scale, and so on, and so on, and so on. So I have faster and faster oscillations. Okay? Even easier is this situation. I have 1, 2, 1, 2, 1, 2, and then I make the width of these layers smaller and smaller and smaller and smaller. And in the end also I G-converge to something. Okay. Issues here. So it's clear that these functions are highly oscillating, so they don't converge in any pointwise sense. Okay. So this shows that I have an example where the Dirichlet normal map they go to 0, but however the difference between this sigma h, which oscillating say between 1, 2, 1, 2, 1, 2, and the identity, is going to be always. It's not going to converge. Okay. So recently we look at this, since we were interested in this stability with Alberto Ruiz, we look to these questions about to which extent this is true. So to which extent G convergence implies the convergence of the Dirichlet normal maps. Okay? Because here it's really important that they are the identity here and that they are the identity in the end. For the proof is built on a explicit calculation in the end with the spherical harmonics, which are solutions to the equation here with identity. So this is pretty much a work in progress, but something we can say is the following.
Daniel,
Yeah.
in this situation, you can, if your what's it called, age coincides with the final, I mean, it does oscillate, then in this part, what you call this?
In this, yeah, two-layer neighborhood.
Is that we want to converge, right? All the solutions
You mean that the solutions will converge strongly there?
in this
Yeah.
areas where it is I.
Yeah, I think so. I should think about this, but J-convergence in principle is a local concept. So, yeah.
So
Okay, without having it checked before, I would say that yes. I would say that yes. Okay. So with Alberto, we could do so far the following. Say omega smooth, n equal to 2. And essentially what we could do is replace the image map identity by any map sigma. So it would be a similar situation, a little bit more rougher domain. And here it would be sigma. And sigma, say, for the time being is C2. Okay? And then, so this is the sigma h. They do what they want to do inside, but they are equal to this unity map sigma. And now sigma h G converges to sigma. Okay? Then we have the convergence of the Untitled maps. Yeah. It's the same, but the only difference is that we replace sigma, the identity, by sigma. Okay? But however, as I said, it's at this way we couldn't make their proof to work because they really use spherical harmonics, and we use a different argument, which I think it might have some interest if somebody hasn't done it before. Okay, so this goes to 0, and here this I put it to be on the safe side because we don't know still. This requires some properties of the Poisson kernel. So for omega smooth and sigma C2 they discuss it, and probably one can react this regularity. Okay, so this is with Ruiz and it's in progress, hopefully. Yes. Anyhow, okay, a remark here is that then one would conjecture, okay, then this G convergence always implies the convergence of the corresponding Untitled map, right? Because we are all the time assuming this on the boundary, but why do you need this? And the answer is that in general this is not true, because of a remark, not true. G convergence implies convergence of the n because of stability at the boundary. Okay, because something that I found remarkable about this, so here this stability of the boundary.
So can you please use some details so we see?
Yeah, okay, because probably it's not so easy to. So it's not true that the G convergence implies, so this result is not true without any extra assumptions. Okay, and the reason is stability of the boundary. So it's known that if the Dirichlet-Turing map converges, goes to 0, then at least in the boundary, this tends to 0. This, for the smooth case, it follows by the paper of Silvestre and Ullman of 86, and also for more irregular domains, the approach of Brown, and probably the approach of Alessandrini. And the important thing here is that you don't need a priori control on the oscillations. All the stability results that we see, you have that gamma is controlling some C2, or in whatever norm, there is an M here, so the oscillation is controlled.
So once again, repeat.
Yeah.
Because in your case, sigma n is equals to sigma, so, right?
Yeah. So in my case, this is not, otherwise the theorem would be false. Mm-hmm. But what I'm thinking is, okay, I have to assume this. Mm-hmm. Now, is this stupid or is needed in some sense?
Right.
And then the theorem I would like to prove is like this. Let be sigma h, which G converges to sigma, then the Dirichlet-Neumann map converges.
But that will be probably true if you make some weaker spaces.
Okay, that's I don't know. But again,
Not H1 half, but something.
let me tell you my argument against.
Okay.
So my argument against is the following. We know that there is a stability at the boundary.
Yes.
And the stability at the boundary does not require any control on the oscillation. So it just needs regularity, but not control on the oscillations. So now take this G convergence sequence and make them that in the boundary they don't converge. Okay? Then you will, if the theorem would be true, I would have G convergence, convergence of the Dirichlet-Neumann map, and then convergence at the boundary. So contradiction. So whatever result you get here, it should be such that it doesn't imply stability at the boundary. That was my remark.
So you mean that if it would come to the boundary, then it would be not true because of that result, right?
Yeah.
If it oscillates at the boundary.
Right. So my hope was to prove that the sigma h converges to sigma at the boundary, and the G converges, then you get this result. But I don't know how to do it. Okay. So we have to show that they are really the same in a tubular neighborhood. And I'm not even, by looking at radial examples, it's not even clear that it would be true. But as I said, it's to be seen. Anyhow, so we have some, oops. So I have given another bad news. So this by new, this G convergence examples, as you see here, they can be made. Here I made them with jumps, but they can be made C infinity. Okay, so it's not an issue of continuity, but it's an issue of oscillations. So they oscillate a lot. So you need to have some control on the oscillation, and this is also what we learn from this abstract argument of Mandaji. So that if you control in some sense the oscillation, there is a hope. At least we don't have a counterexample. And which is the best way to control the oscillation? A natural way is this fractional Sobolev spaces. So we come to a third good news, which says that if omega is ellipsis, and now these conductivities are still strongly elliptic, but I control them in some Sobolev space. Okay, let me put 2, but it's not important. Then indeed, I can control the A2 difference in the full domain by what is doing my Dirichlet-Neumann maps. Okay, what you said before, this is true. Of course, you could put some weak topology here. That's just the definition. Okay, this is the theorem, I think, gamma Lipschitz, and this was with Klopp and Ruiz last year. And then a part which we were not satisfied, I was not satisfied at this, is that the omega is Lipschitz. Because in the Astaga-Paivarinta result, omega is any domain, anything, okay? So with Rogers, we look at this, and then we could prove that a similar result holds as long as the, okay, it's not so important what it is, but the upper Minkowski dimension of the boundary is smaller than 2. Okay? So this means, what this means? This means the following. That the limit, I take parallel neighborhoods of the boundary of size delta, and I measure them. I take the for alpha greater than 0. Okay, this is just a definition. Okay, let me just continue. So we could put here, this is the biggest of all these dimensions that one finds in geometric measure theory. So the Hausdorff dimension and all the others are smaller. So if any reasonable dimension of the boundary is smaller than 2, then we get also this stability. Okay? The best way to look at this is the definition because it is good for our purposes, but this is simply to count how many squares of diameter delta do you need for covering your set, and then compare them with data to the n.
N is 2 here.
N would be 2, yeah. Yeah, thank you. Okay. So in this sense, somehow this is more parallel to the result of Asta and Pivarinta, which work for any domain. This also works for almost any domain. Of course, I don't have any answer for, in practice, what would be your inverse problem where the dimension is fractal. But I don't know, one could think that the Earth is very corrugated, and then you could consider it to be fractal. And then to do this result is a corollary of this one, plus this following last theorem, which is the regularity of the characteristic function of a domain. So it says that this norm is controlled by this integral.
Then let's go to the previous one. In this theorem,
yeah,
that is stability theorem, the previous one, do you assume a priori the dimension of n of gamma 1? It's just boundary. It's just boundary. It's
yeah.
method. Yes. Mm-hmm.
Okay.
But I guess this dimension will go into continuity modules, right?
Yes. What it will happen is that, so in principle, the continuity modulus, okay, I come to that, will depend on the fractional sovereign space I am having here, on this epsilon.
Mm-hmm.
And now what I am showing is that the characteristic function of a domain with such a Minkowski dimension, it has this control, or it belongs to this fractional sovereign space.
Mm-hmm.
So what I'm going to do is to consider a new conductivity, which is, say, gamma 1 times the characteristic function. And then it will be in the sovereign space which is worse, either the sovereign space given by the domain, or the sovereign space given by its own regularity.
So it's W what?
Alpha P.
Sorry,
Alpha P, yeah. Okay.
And they're the same alpha?
Yeah, the alpha is...
It should be the same alpha for that.
This is this alpha, and this is this alpha.
Yeah, and this is the same as that?
And this is this alpha, yeah.
Mm-hmm.
Okay. And then let me just say that once we were looking at this, we wanted to understand what is this characteristic function, and then we could get a result which I think is new, is that, because, okay, let me say everything.
Why do you need this upper bound dimension d omega?
Because if this dimension is small, then this characteristic function belongs to this space. So what I mean is that the characteristic function belongs to some fractional sovereign space.
But I mean, if they put here 1, it will be the same. It's actually 0 that you see by thing, correct? In the integral of the right hand side.
Sorry?
The upper bound of this integral is dimension d omega, right? But it's actually only delta close to 0 that gives you...
No, thanks. This is not dimension, this is diameter.
I see.
Thanks. Yes, diameter. Okay, but coming back to this, we saw that this is in true, is not generally they are the same, but if omega is what is called the quasi-ball, they coincide. And then we were researching in the literature, and then it turns out that Sickel has been looking at this problem for some time, and then he obtained also a different proof of this upper bound, but I think this result for quasi-balls is new. Quasi-balls are snowflakes. So the most The traditional quasi-void is a snowflake, something like this. And then, okay. But anyhow, this is a side remark to the inverse problem. So, summarizing, we have that you need some control on the oscillation, because otherwise the stability is not true. And now if we measure this oscillation in the terms of fractional survey of space, and then we require a very mild regularity on the boundary, then we have an A2 stability result. Okay? And so this is, and also in terms, this gives some new results on the characteristic function of the boundary. Okay, I have 15 minutes. Maybe I spend some ideas. Let me just say, because I won't have time to say it when I finish the talk, because I'm running out of time, that there are many questions one can ask here, but I think the most important, or the one that I think is crucial, is to have that this stability, instead of being global in the full omega, it would depend on how close you are to the boundary. Because as I said, the stability at the boundary is very good. It's even gifted. And the stability in the interior is very bad, it's logarithmic. So, I don't know. What I think it would be a major breakthrough here would be this, to have some stability results which depends to the distance to the boundary. As far as at least I was reviewing this proof before, and I don't see how to do it. So. Anyhow, so since I don't have much time, what I'm going to do is tell you a little bit of this different approach that we took with Alberto to understand this convergence of the Dirichlet-Neumann map, and maybe something on the proof of the stability result. At least to mention that we solve also in the way some open question on the decay of the so-called complex geometric optic solutions. Okay. So for the comment on the convergence, so in this we follow the strategy of Sandrine and Khabib. Till some point we have to do something different. Okay, so I have to estimate lambda gamma h minus lambda gamma, the operator norm, and then what I do is choose spherical harmonics at the boundary, and create a... Not needed, not really. I just need really eigenvalues of the corresponding Laplacian in the boundary. Okay.
But then this boundary should be not particularly bad.
Yeah, that's why I had to put this omega smooth in sigma not so bad, and then we don't know how much we can relax these two properties. Okay, and now this will be the soup of u's with h1/2 norm equal to 1 of lambda gamma h minus lambda gamma u times u. And I write these u's in its basis, okay? And I put them there, and I have a double sum in M and in L, in M, in L, and then this bilinear form, lambda gamma h minus lambda gamma IL IM. Okay. Now what do I gain from G convergence? The very definition of G convergence tells me that. Sorry? Thanks. Okay. What means G convergence? It means the following. G convergence tell me that what is called the convergence of the fluxes. So now I should read carefully. Now correct. And the else S and M means that so these U's are related because they solve the corresponding Dirichlet problem with the boundary value given by these generalized spherical harmonics. Okay. Okay. This is the precise definition of G convergence. In fact, if the sigma would be not symmetric, that would be the H convergence of Tartar. Okay. And remember that this is the definition, the very definition of the Dirichlet-Neumann map acting on this UL and UM, okay, of this form. So this is precisely this minus this. This is precisely this animal here. Okay. So this tells me that at least for a finite number of items here, I don't have to care because they will go to 0 by definition of G convergence. And that's why, so I have the m's here and the n's there, M, L, and there will be a big L and a big M where I don't care. So I just have to show that the tail goes to 0. Okay? So you have to use, I say it again, you use G convergence to prove that for a finite number of terms you don't have to care. And then to have the convergence of the operator norm, you have to show that the tail also vanishes. Mm-hmm. And for that is where you need to use that the competing conductivities, they are the same in a tubular neighborhood near the boundary. So I will only show you this. So it be epsilon L equal to this. Switching to the time project from. So it's norm as an element of h minus 1/2. Okay? And then I claim that this sum is finite. So in particular, each of them goes to 0, and then when you put this into this big sum and manipulate properly, you get that the tail goes to 0. And why this is true? This is true because it can be proved that this is controlled, by the gradient of UL square on precisely on omega prime, and this is the key thing. So recall I have omega, and I have this omega prime, which was a compact subset of omega, and I knew that the conductivities were the same outside here. So when you write this definition and put it, then you get that this is controlled, constant here of course, and not only by this gradient, not only by the gradient, but only integrated in omega prime. Okay, so it's an interior estimate. And now we can use Harnack's inequality, and this is controlled by the A infinity norm in some other compact set, but maybe different, but also strictly included in omega. Okay, and now you write what is this. Okay, so this is like this. So now I want to write this sum. Okay, no, maybe I do it here. And now I express this so this is essentially sub in x of UL of x, all of it squared. And now I write UL using the Poisson kernel. Okay, so this would be, the sub would be the same, but UL would be the integral of the Poisson kernel x minus y against YL. Maybe let's just do this and then we save time. Okay, so at each point, UL of x, I express it in terms of the Poisson kernel. Okay, very good. So this is how it is, and now I put it in the sum. And the sum would be the sum of the integral of PLx minus y YL dy squared. But what is this? This is okay, sub in x. What is this? Now I use that the UA is a basis on the boundary, and PL for each x, PL of x minus y is an A2 function with this regularity. So I get here sub in x of PLx. Sorry? Yeah, where is this L? It's Poisson kernel. In fact, it should be P gamma because it depends on the gamma. Okay? P gamma, thanks. P gamma, and then I have here A2 of the boundary. Okay? And I haven't done anything, but I have shown that this is, with this regularity, the Poisson kernel behaves quite well, and this is then finite. And that's what I wanted. Okay, the sum of this epsilon area squared, which are these difference to the Autonoma map, is shown to be in general without regularity finite. Okay, and it all depends on how good will be your Poisson kernel and how flexible will be your basis of eigenvectors in the boundary. Okay.
But now you take the sum, correct? And the sum will be.
Now I haven't finished the proof. Now I know that this epsilon L, that I have that this sum of epsilon L squared goes to 0, and then I put this up there and use Heider inequality a few times and then get it. But it takes more effort. Okay.
Sorry, I somehow missed the point. Now, what is written there is basically the proposition of P gamma with respect to the eigenfunctions, correct? So
Yeah.
you basically have the whole sum. You take this, right.
I'm using here, sorry, Plancherel.
I agree.
I'm using Plancherel here.
Yeah.
So it's simply Plancherel. Okay. I think it's a new point of view, and it's interesting to see how far it goes. Okay, so I was planning to tell you the whole proof of this stability, but I think you will escape without this because it's already 3. So let me just tell you, because I think it might have some interest, that a couple of remarks on our proof. So somehow the proof of Asta and Paivarinta follows the previous approach on scattering transform, but one, they are able to construct complex geometric optic solutions without regularity and to show that they decay. And second, they have a very nice, so one exists CGO, so they are of the form EK phi k offset, phi k, and then they can show that, so they don't decay. You see what I was showing at the beginning of the CGO construction of Sylvester and Ullmann. There was an A and a remainder, and the remainder goes to 0. Here there is if you write it in this form, the remainder doesn't go to 0. But at this it goes to 0 mildly. So we can show that if gamma is in H epsilon, then we can quantify this. It's a constant. A universal constant which depends on ellipticity and sin C epsilon. And this was conjecture, and there was some numerical evidence in a paper of Asta, Müller, Paivarinta, and Seitanen, I believe, which are trying to run the numerics corresponding to this. And I could see it in the computer that this would be the case, but we were able to give an analytic proof. And the second thing I want to mention, which I think is the one that passes me more, is that you take these U's now, and then it's not hard to see that they solve a so-called pseudo-analytic equation where you differentiate them respect to this k parameter. It's not hard to see once somebody tells you that this could be true. Okay? And then this is the previous thing, and this depends on Z and on K. And in general, the previous approaches, they say, okay, and then there will be unique. This is a parameter which is determined by the Dirichlet-Neumann map. So uniqueness. The Dirichlet-Neumann map are the same, the scattering transforms are the same, and therefore, if this equation would be good, the U's are the same, and the end of the story. But however, what happens is that here you cannot do this in this way with only one equation. You need to consider what happens in Z and in K at the same time. Okay, and I think this is different from what they have done before. So it's not that I look at this equation, which is an equation in K, and I have uniqueness. But if I look at the whole family, I have uniqueness. And then we could quantify this. And quantifiable. Somehow I have spoken about this several times, and I never get to this point, which I think is the deepest, but okay. That's all. Thank you.
Questions? I have a question. If you go back here, so no, not here. You do it about this gamma convergence, right?
Yeah.
So you have a conjecture, something like that. If you have,
Yeah. So it was this issue where
if you have sigma n goes to sigma, no. Now lambda n goes to lambda.
right, yeah.
Lambda n goes to lambda. Dirichlet-Neumann maps goes to lambda, right? And then sigma n gamma converges to sigma, and the boundary sigma n converges to sigma, just converges to sigma because of the boundary continuity.
No, but my conjecture was the other way around.
But they proved that conjecture.
They prove.
You proved.
Well, to some extent, yeah,
so
with not fully.
You have conjectures and options around that.
part of
that
it,
if you have that, then obviously sigma on the boundary, sigma n turns to sigma, or gamma n turns to gamma, but then gamma n turns to gamma in the sense of gamma convergence. That is weaker, but I don't think we need to be sure of that.
No, there is this
And
issue.
then the a priori condition would be that just they are bounded in gamma,
There is this issue of that this fact of being isotropic, is not a stable energy convergence.
Sorry?
The fact of being isotropic.
Yes, I know.
So then I think this somehow.
But you see, on the boundary, it's okay.
So they are the same on the boundary,
Yes.
and the Dirichlet-Neumann map converges. So you are saying that always we will have the convergence of the.
You know, somehow your priori no, but your sigma, your gamma correspond to some isotropic activities.
Ah, okay. Okay, then. Okay. Okay, yeah. Yeah, I always rule it out because of this anisotropy, but if you priori, yeah, why not? Yet, let me come back to this tomorrow, and I will answer to answer.
Other questions? Thank you very much, and we have a coffee break.